welcome to the first in a series of videos for statistics. This is section 6.1. The series of videos will be covering the important sections from chapter 6. Be mindful that it will be the third video, 6.3, when we're dealing with population proportion. That will be most closely aligned with your term 3 project. When we get to that video, I will be making some comments that will help us to change some of the dynamics of the project so that it can be applicable to our current online situation. For distance learning purposes, while I don't typically collect homework, we will be assigning daily assignments. You're to watch the video and then complete the problems as assigned. Upon completion of those problems, you will find on My School app page there will be an assignment where you can upload a PDF of your work. I'll be looking for those assignments to be uploaded by 9 p.m. Of the day in which the assignment is given. For 6.1, we're actually going to separate your work into 2 parts. So due yet this evening will be pages 305 to 306, numbers 5 through 32. And then tomorrow, the 24th, page 306, 33 to 55 odd. Of course, you know the solutions are on the My School app page for the text, so please feel free to be checking. But when you do upload your work, I do expect to see work for these problems. I will not be satisfied with simply the answers. And you all know that, and certainly where appropriate, which is pretty much all the time, we're going to start with a sketch. Now, also on the My School app page, please pay attention. There is a discussion assignment for chapter 6. This is where you're going to enter any questions that you have regarding the assignments or any of the material in the sections that I'll be teaching. If you have questions as you're moving along, please enter those questions in the discussion assignment and I will respond to you. Also, if you have not come into school to pick up your belongings, because as seniors you certainly left well before these changes were put into place, you're going to need to come in and get your statistics book. To help us along for the first few sections, I have created PDFs for these 3 sections, 1, 2, and 3. They are found inside that discussion assignment. You certainly can click on those and you can get the pages, but I haven't included the tables. I haven't included any answers that would have been in the back of the text and that kind of thing. So it would still be in your best interest to come in and get your own textbook. So let's begin. 6.1, confidence intervals for the mean. Now section C, we already started to talk about this. Section D, we didn't meet before you all left on your spring break. So some of you will have some recollection of me making a few comments about this, but this is for everyone to understand. Confidence as a word decides, well, how sure are we of something? And as a statistician, we want to be extremely responsible. And so we're very careful about making bold statements about individual values. So we understand as mathematicians that oftentimes it's more responsible to talk about an interval, to talk about a group of numbers where we feel certain or confident that a particular measure occurs. Now remember, we're using sample data and sample analysis, descriptive statistics, to make inferences about populations, inferential statistics. In 6.1 and 6.2, we're going to be working with that unbiased estimator, that point estimate that we know as mu, which is the mean of the population. And we use x bar as the sample, where this is the population, this is the sample mean, and when CLT applies, that central limit theorem, when n is greater than or equal to 30, we've already said that the distribution of the sampling means equates to the pop mean for samples that are large. But to suggest that with any certainty that this is true as a point estimate, again, that would be a pretty bold statement. the likelihood of this being true is virtually zero. Okay, so again, as a researcher, we have to live within that reality. And so rather than trying to make bold statements about individual points, instead we move towards intervals. If you're following in your textbook, which I hope that you are, we're on pages 288 and 299. Definition of an interval estimate then is an interval or range of values used to estimate a population parameter. So for the time being, we're going to be dealing with mu, which is that population mean, and we're going to be looking at its sample corresponding value, x bar. You'll notice that beyond standard deviations, or what is now going to be considered margin of error, and we're going to talk about that, we have probable values within the interval and improbable, what we would know as unusual values, outside the interval. So in order for us to proceed, we need to think in terms of this level of confidence definition. The level of confidence C is the probability that an interval estimate contains the population parameter. The level of confidence, again, the wording here is extremely important. The probability that the interval estimate, x bar in this case, contains the population parameter. In other words, is it really there? How confident are we that that estimate lies within that interval? Now you'll notice our study tip, our gal on 299, she sits there and she's smiling because she knows that industry standards confidence intervals are 90%, 95%, or 99%. This is not to suggest that we couldn't calculate others, but this is what's typical. So let's take a look at the 90%. That refers to the middle 90%. So looking at our normal distribution then, to get the middle 90% implies that 10% is shared with the right tail and the left tail. Well, that being the case, we have what are called critical z values that are associated with those locations. And you can see in your textbook, for 90%, this is 1.645. We've seen this before. And we talked about it because we said, well, you know, there will be a time when we're going to need to know these. Well, we're here. For 95%, the picture changes a little bit. Again, for 95 to be in the middle means that we are sharing 5% in either tail, 0.025, in either case for this, and the critical z is 1.96, and it's opposite, negative 1.96. Last but certainly not least is the 99%. Well, the middle 99% then gives us 0.01% to be shared, or 0.01 or 1%, so that's 0.005 in each tail, and the critical z at 2.575, and its opposite, negative 2.575. So these are values you need to know. You should really memorize these. Now, these aren't the only ones. If we ask for an 80% level, well, you would draw a similar picture, only you would have to use your normal CDF or your inverse norm, as it turns out. If we were asking for middle 80% and we want the z-score, if it's middle 80, that means I've got 20 to share, which means this is going to be 0.1 and this is going to be 0.1. So I've got what? 90% to the left. So I'm going to inverse norm at 0.9, 0, and 1. And that's going to give me the z-score that's associated with something other than the industry standards at 90, 95, and 99. Just remember, we're building an interval about the center. If we're trying to find mu, that would be the physical middle, and then we're trying to discern where these endpoints would be for said interval. So again, you take whatever the confidence interval level is, it becomes the center, take the difference between that and 100%, divide it by 2. That's what's in the tail. Now we're always, of course, measuring to the left. So in this case, 0.8 plus 0.1, that's how we know here to use 0.9. But please memorize 90%, 1.645, 95%, 1.96, and 99%, 2.575. You'll notice all of this has been derived for you on the bottom of page 299. Now, how do we create the interval? Well, let's talk about that. How do we create the interval? Well, when sigma is known, well, what's sigma? Sigma is the population standard deviation. If we know that, that's very powerful, and to be honest with you, that doesn't happen very often. But if we know that much of the information, then the margin of error calculation is really pretty sweet. It's pretty easy. We're looking to create a scenario where we are evaluating this interval, which is going to exist in such a way that the endpoints, if you will, and again we use parentheses, not brackets here, is plus or minus the margin of error. And the margin of error then is a calculation that says, well, find the critical z. Well, what's the critical z? Well, that depends upon the confidence interval level. So these are the z-scores that we either have memorized because we're using industry standards, or we've inverse norm to find using the middle X%, whatever it was. And we're going to take that, and then we're going to multiply that by sigma over the square root of n. Now you've seen that before. That was that standard deviation of the sampling distribution. Okay, so again, we're not making stuff up brand new. This is coming from the prior chapter when we did the sampling distribution. And we said that the sigma for the sampling distribution was the population standard deviation divided by the square root of n. So given a particular scenario, and again, CLT has to apply here. Either the sampling size has to exceed 30 and or the population needs to be normally distributed. You're very welcome to read, and I encourage you to do so, something such as example number 3, which shows you then how to calculate the margin of error in order to find the endpoints. The other thing that I would point out to you is on your TI 84. Lucky us, once again. We've had some pre-programming done for our benefit, which allows us to input data, and it will actually create the confidence interval for us. If you look in your stat menu and you go over this time to the tests section, in the tests section, we have at item number 7. Item number 7 is called the Z interval. Item number 7 is called a Z interval. So again, we're using the stats button, and we're using the test drop down, and we're choosing item 7, which is the Z interval. Then what kind of information do you need to provide? Well, you have two options. You could go directly from the list and enter data. We typically don't do that, but you could put your data, raw data in L1. Normally, we'll be using stats, so you want to make sure that that's highlighted. Again, the pop standard deviation needed to have been given to you in the problem, so you're going to pull that. The mean of the sample, either you figured it out or it was again given to you in the problem. That's an input on your part, as well as the sample size, n, and then it's going to ask you for the CI. The CI is the C level, I guess is what they're going to say in most of the versions of the calculator at this point. The C level is going to relate to the level of confidence. For example, 0.9 for 90%. And that's it. When you enter that in return, it's going to actually calculate the margin of error for you. It's going to add it to the mean, it's going to subtract it from the mean. And it's going to give you an answer in parentheses, which is the lower and the upper bound. So it's going to correspond directly to the kinds of answers that are required for the problem. Example number 4 on page 302 will take you through this exact discussion. You'll notice the green box on 302 follows this set of instructions to a T. Now, I take your eyes to the bottom of page 303. This is very important. It says, after constructing your confidence interval, it is important that you interpret correctly. The correct way to interpret a confidence interval is to suggest that we are 90% confident. With a 90% confidence, we can suggest that the mean is within that interval. With 90% confidence, we can say that the mean is within that interval. So we want to be very careful. It is incorrect to suggest that the population can move, or that the population mean, I should say, can move. That's not the case. The confidence has to do with the interval over which we have provided. I've told you guys before, I'm not a dart player. My son-in-law is an excellent dart player. And if I'm asked to play darts with them, they run and hide because they should. I have a hard time hitting the mark. So I want to think about that as a metaphor when we're building confidence intervals. If I say I'm 90% sure that I'm going to hit the board doesn't need to be that big, does it? But if I increase my confidence, if I'm staking a claim that I'm 95% sure I'm going to hit that board, if we're talking about me here, we need to increase the size of that dartboard. And then if I would have I'd have to be out of my mind, but if I said I'm 99% sure I'm going to hit that board better be about this big. Because otherwise, more than likely, I'm going to miss. So why do I tell you that? For the same set of data in your project when it comes up, we're going to be creating confidence intervals. Make a note to self. The higher the confidence level, the broader the interval needs to be. So when you're doing your calculations for homeworks and whatnot, be conscious of that. That margin of error needs to grow. Well, of course it doesn't. How is it going to grow? Because what's changing in the calculation? Well, the critical z value is going up. See, it only needed to be 1.645 at 90% because the dartboard only needed to be this big. That margin of error could be smaller. However, if I'm this confident, I better be using a much larger critical z value in the margin of error calculation, because that's going to grow that margin of error. That's going to push those boundaries out a bit further. So bear that in mind as you are doing your calculations. Last thing for the section, over on page 304, finding minimum sample size. Again, as researchers, when we are developing our samples to create trials, we want to make sure that we are being responsible with sample size. And we know that the larger the sample, the smaller the standard deviation. We talked about that in the last chapter. And so intuitively, I hope that you still understand that to be the case. But if you look at the minimum sample size over on page 304, I want us to look at this margin of error again. The minimum sample size can be determined by an algebraic manipulation of the formula. Error equals z sub c times sigma over the square root of n. Well, this time I'm going to solve for n. So I'm going to multiply both sides by the square root of n, and I'm going to divide both sides by e. So I now have the square root of n equaling z sub c sigma over capital E. Well, I don't want the square root of n, I want n. So I'm going to square both sides. And this is where you find the definition then in the text, n equals z sub c sigma over capital E quantity squared. So if you know the confidence level, you can find the z sub c. If in fact you know the sigma, population standard deviation, and if the error has been articulated in the problem, you can find the minimum sample size. Please take a look at example number 6, because I want you to understand how to find the e-value when we're looking at the words. The economics researcher wants to estimate the mean number of hours worked by all grocery store employees. How many employees must be included at a 95% confidence interval, so boom, Z sub C 1.96. We knew from a prior example that the population standard deviation had been given at 7.9, but the last piece says within 1.5 hours. So when you see wording like that, within 1.5 hours of pop mean. Within means plus or minus 1.5. That's E. Go ahead and use the positive. It wouldn't matter if you used the negative because we're going to do what with it anyway? We're going to square it. So this kind of language is E. So when we're doing homework problems and we're nervous because we understand what Z sub C might be and we understand where sigma might come from, look for the language that talks about what the E value is going to be. This concludes the discussion for 6.1. Today is the 23rd of March. By this evening, 9 p.m., we're mandated to have our homework in via PDF. I have an assignment on the My School app page. Please load your PDF there. I'll be looking for it. Use this video also then to help you with tomorrow's assignment, 33 to 55. This ends the discussion for 6.1.